So it's interesting that there was the question about if you have 4 shirts and 3 pants, how many outfits can you make? This is lecture 9 of Math331. So my daughter and I were talking about that this morning, except we did 5 shirts and 3 pants, because I had used that example in probability. And I said, if you're daddy, the answer is 15, 5 times 3. But if you're Kayla or mommy, it's a little bit less because you have to worry if things go. And then Kayla said, actually, no, Daddy, I'm more with you. I'm closer to you than Mom. And then we talked a little bit, and then we said, well, actually, if it's Grandpa, it's actually -1 or 0, because none of them would be considered matching for her. I would have to go to the store, or she would have to provide something.
So you have 5 shirts and 3 pants?
Yes.
I think it'd be 2 to the 8. What?
No.
You can't wear multiple shirts.
Yeah, you can.
Well, no. So I will go with this. So this now is the question of what do you define by your wardrobe? I have a shirt and a T-shirt on underneath this, so I am doubling up. And you could say order matters, right? So when you were giving your answer, did order matter for you? No. So all right. So now here's the question.
I'm so sorry.
If people want to override, but now here's the question: you have 5 shirts. Well, the chart had no desire to do this. 5 shirts, 3 pants. How many ways? We will make some assumptions. You will not use shirts as pants. You will not use pants as shirts. Okay. I'm sorry, it is a strong assumption with some people. Are there any people who are friends of the TV show, fans of the TV show Friends? Yeah. Do you remember the episode when Joey goes Commando in Chandler's outfit?
What if we did?
Right. I am so glad the video is focusing this way right now. So we have to decide what will we allow. So you can wear any number of shirts or pants, including...
None.
Right, so we may have to subtract 1 at the end, but right now we will allow you to have no outfit at all. Will order matter? Yes. So we have the 3 pants. So now here's my question. How many ways can you wear up to 3 pants?
4.
Well, now order matters. Yes.
So we didn't assume that there's only one way to wear a pant?
Wow.
So this is college. We are assuming at this point. No, you could go left leg, right leg. You could go right leg, left leg, or you could do the, if you want. In terms of how you put them on, that's
I
fine.
don't know how you put them on, but what if you just put them on one leg?
Yeah.
And then
Yeah.
another one on it.
We're going to make some simplifying assumptions. We'll be, I guess, like economists. They may not be reasonable for all members of the class. But we will assume that there's only one way to wear pants, and amazingly, you can put them on in any order. So here's a good question. How many ways for the pants? How would you analyze that? This is clearly not something I prepared.
3 ways to wear 1 pair.
Good. So let's do by the number of pants. But before you do 1 pant, what should you do?
No.
Right. If no pants, 1 way. If 1 pant, 3 ways. If 2 pants,
3.
No.
Just pick the pant you don't wear.
Order matters, though.
order matters. It matters which is on the inside, which is on the outside.
6.
And how would you view 6? How would,
3 ways and 2 ways.
well, how would you write the number 6 in a mathematically illuminating manner?
3 factorial over 3 minus.
Yes, 3 factorial over 3 minus 2 factorial, or 3 times 2. So we'll do 6, which is 3 times 2 ways. No, because if we had more pants, this would be, and then if 3 pants, how many ways?
3 factorial over 0 factorial.
Yes, so it's also 6.
Yeah.
So now it's just 3 times 2 times 1 ways. And so the grand total is 16. So So does that number look interesting to you? When you see 16, what do you think? 2 to the 4th. So is there really a 2 to the 4th lurking here? So?
Kind of. Well, I don't know if it's right, but there's 3 pants.
Right.
And 1 not pants. And so, and so for each.
Well, no, because yes.
So it's like the number of like subsets of three elements
But you gotta be careful because how many subsets are there of 3 elements?
of 2 to the third.
2 to the 3rd, there's 8. Because when you take a subset, order doesn't matter. All right, so let's get more data, right? It would be great if we had a number larger than 3. Oh, good, we do have a number larger than 3. We have 5. All right, so now let's do shirts. If 0, how many? 1 way. If 1, 5 ways. If 2, 5 times 4. If 3, our pattern is hopefully obvious at this point. If 4, 5 times 4 times 3 times 2. If 5 times 4 times 3 times 2 times 1. So this is 1, 5, 20, 120? Oh, sorry, 60, sorry. And then this is the 120. And this is 120. And so what do you get? 325. 326. Right. So this is enough to immediately destroy the idea that it's a nice power of 2. This is the problem with looking at small numbers, is you can be easily misled by small data. Fortunately for us, the Windows on William Part 2 is on Monday, not today. So what's the formula if have n? Yes.
The summation as sine I goes from 0 to n of n factorial over n minus I factorial. Or, we'll start I at 1, I think, actually.
Start I at 1 and add 1 at the start.
Well, let's see.
If you have 0, it still holds.
No, if I equals 0,
Oh, yeah, then
it's just
then it works.
Yeah, wait, do we just want to go to n over?
This is good because when I equals 0, we have 1. When I equals 1, we get n. When I equals n minus 1, we get this. When I equals n, we get this. So that would be the formula. Okay? We would love if we had like I factorial down below because we could then have a binomial coefficient, but then that would involve multiplying by I factorial over I factorial. I has dependence, so can't quite do that. So the question is there a nice expression for this sum? How does this sum grow? What kind of bounds can you get? As n gets very, very large, how much is the last few terms going to be relative to everything else? So as extra credit, analyze. Actually, what should we do now for this? For this, we have this new sequence. We will call it the Commando sequence. What should we do for the Commando sequence? Plug in the online Encyclopedia of Integer Sequences. So I'm just defining right now a function Mathematica. It's one of the reasons I keep it open at all times. Okay, so the function is going to be the sum of n factorial divided by n minus I factorial. I goes from 0 to n. Okay, for n equals 0, n less than equal to 6, n plus plus, list equals append to list f of n. Okay, and so the first few terms I get are 0, 2, 6, 12, 20, 30, 42. So that does not match what we had. Oh, oops, there's a typo. Okay, there you go. Okay, so now I've got 1, 2, 5, 16, 65, 326, 1957. Okay, so let's test the online Encyclopedia of Integer Sequences. I am going to it right now. Note main page. Right. Search.
Wait, did you say 1957 was right after 3?
26, yes. Okay. It was just okay. So it says displaying one of one relevant results. Total number of arrangements of a set with n elements. Okay. So it is there. It has an enormous amount of information. It has references. It has links. I'm trying to see if it has an asymptotic formula.
Well, so the recursive seems to be just multiply.
Yep. There is a very nice recursion relation. And then it gives some type of generating function. So there is so much stuff here. It's hard to tell exactly what's the most useful stuff. Asymptotic result due to Ramanujan. Right. N factorial times e minus a of n is approximately 1 over n. So it's saying if n is large, it's about. It said n factorial times e.
Yeah, wait. Oh, because if you so n minus I equals I, right?
Yes.
For factorials, because you're summing them all.
Right.
So you can rewrite that as n factorial times the summation.
Yep.
As I goes from 0. Yeah.
Yep.
Wait, why does n minus I?
Just pull out the n factorial.
Yeah. No, and then Oh, that's nice.
So if you pull out the n factorial, then what you have here is when I equals n, you get 1 over 1. When I equals n minus 1, you get 1 over 1. Then when I equals n minus 2, you get 1 over 2 factorial. This is just the terms of the expansion of e. But now you're starting with the largest one. So this is why you will get approximately e times n factorial, and that's where you'll even get the error term from. Yes?
So do we all get extra credit?
No, but you are now welcome to wear multiple layers of clothing to class without having your wardrobe choices questioned. So I've been thinking about, when we had this, about pulling out the n factorial. But it's interesting, when you have it written the other way, when you start off with the lower values, the pattern is much clearer. I want the 1 over I factorial to make it look like the binomial coefficients. We should be looking at 1 over e. This is the power of something like the online encyclopedia. As soon as you see something like that, you then have an idea of did you have that beforehand?
I had it before, yeah.
Actually, you should have spoken up. I'm sorry?
I should have.
Yeah. So remember, email me when you make good comments in class so I can put these in the gradebook. So when I write letters of recommendation in future years, I can remember and say specific things. So include that, email me today. There are people who email me after, say, 4 or 5 years and they need a letter of recommendation. If I've written one for them in the past, it's not a big deal. But if I've never written one, it's nice to have some notes. All right, so this was a nice diversion. a nice example of where it comes into play. I'm hesitating to say if anybody questions your wardrobe choices later, please refer them to me. But, all right. So let's go back to Goldbach. So we wanted to talk about writing numbers as sums of 2 primes, or sums of 3 primes, or sums of squares. And we wanted to see how could you actually solve a problem like this. So for the longest time, a lot of mathematicians felt these were problems you just couldn't study. The primes are multiplicative. You can't talk about adding primes. So last time we talked about e to the 2 pi I x is cosine 2 pi x plus I sine 2 pi x, where I is or I am to the square root of -1. And we showed how you can get all the trig relations from knowing this and knowing that e to the x, e to the y is e to the x plus y. And that justifies the series expansions and everything. We often write as shorthand, e n of x is e to the 2 pi I n x. Just a little shorter notation. And sometimes when people are introducing definitions, they put a colon in front of the equal sign to just flag that this is notation. What I'm going to do now is just try to give you a rough sense of what's going on. I'm not going to do what's best in terms of analyzing things with number theory, but I'll do it close enough to give you a sense of what's happening. So we're going to define a new generating function, fn of x, as follows. So do you want to deal with writing numbers as sums of primes or sums of squares? Which do you prefer? It's the same setup. All that changes is when you do the analysis, which we won't do. One becomes harder. Primes. All right. So we're going to define it as the sum of all primes less than or equal to n of e to the px. Really, we should put a log p weight. We should not weight all primes equally. We're not going to do that. We will treat all primes equally. From a number theoretic point of view, it is much easier if you do a small amount of discrimination. And this way, primes that are very small, like 2, 3, 5, aren't weighed as much as primes of size 10 to the 10th, which aren't themselves weighed as much as primes of the size 10 to the 100th. The logarithm is very slowly growing, and putting that weight in there makes it a little bit easier. Has anybody seen the Riemann Zeta function? Okay, so if you've seen the Riemann Zeta function, if you know about the Euler product, when you take the logarithmic derivative of the Euler product, logs come out. That's where the logs come from in this. So let's let a n, do you want to do sums of 2 primes Goldbach or sums of 3 primes tertiary Goldbach? What do you want to do? 2 primes. So an2 of n is going to be the number of ways that we can write n as p1 plus p2, where p1 and p2 are at most n. And then a2 of n is just going to be the number of ways we can write n as p1 plus p2. And we know that that's clearly greater than or equal to a to n n. So in this way, I'm only counting pairs where each prime is at most big N, and in this way I'm counting all pairs. Okay? And clearly, this has to be large, at least as large. It can't be smaller, because it has no restriction. What is true if little n is less than or equal to big N? What's true about these two numbers? So if little n is at most big N, what's true about those two numbers? What's their relation? Yes? They're the same. And the reason they're the same is that the only difference is that in this one, I have to restrict myself to primes that are at most n. Well, given that my number itself is at most big N, it's not really a bad restriction. Right? So the way the problem works is if we want to show that your number has a representation, we will look at this function where little n is less than or equal to big N. And if we can show this function is positive, then this function is positive. So the goal is show a n2 of n is greater than 0 if n is less than or equal to big N. What kind of number is this? So what kind of number is a n2 of n? So it's this count. What can you tell me about a count? What kind of number is it? Whole number, integer number. So if I can show it's greater than 10 to the negative quadrillion, what do you know? As soon as you know it's greater than 10 to the negative quadrillion, it's positive. Okay, well, we already knew that. It's at least 1. So that's the way the method works. You just have to show it's positive. Doesn't matter how positive. As long as it's positive, since it's an integer, that immediately corrects and now becomes at least 1. All right. So the question is, how do you show it's positive? And how do you use this generating function fn of x to help? Well, let's look at some facts first. What's the integral from 0 to 2 pi of e to the 2 pi I n x dx? This is one of the most important integrals. Oops, I want to go from 0 to 1. Well, if we expand this out, this is the integral from 0 to 1 of cosine 2 pi nx plus I integral from 0 to 1 of sine 2 pi nx dx. What do those integrals equal? Where n is an integer. Sorry? So I'm integrating sine and cosine from 0 to 2 pi. Gotta remember your trig. If you don't remember your trig, how should we do this? We then need to remember antiderivatives.
Well, the first one is 0.
Okay.
The second one is, cosine of 2 pi is...
They're both 0, because you're integrating sine and cosine over full periods, right? If n equals 1, that's what we have. This is n equals 1. If n equals 2, right? So you would just be integrating a odd function if you look at it starting from the right place. So the positive areas cancel with the negative areas. So does everyone agree that the integral is 0? You are almost right. Is there any n where the integral would not be 0? Yeah, when n equals 0, what's the cosine of 0? And when n is 0, what's the sine of 0? So what you get is this beautiful, beautiful fact. 0 if n does not equal 0, 1 if n equals 0. This is a detector. It can detect if your number is 0. Okay? So what I'm going to do is I'm going to have you choose a number at random. Did I hear 7? Yeah. Okay. Is your number 7? It better be, or you're lying to me. I mean, all right. So the idea is if you choose a number and it's an integer and I don't know it, so you choose m, okay? I can then look at the integral from 0 to 1, e to the 2 pi I n minus m x dx. And I'll plug in different values of m. I can take n equals 0, 1, 2, 3. And for each one of these, I will compute them. And then I will keep getting 0, 0, 0, 0. And then eventually, when my n hits your m, I get 1. And this allows me to detect your number m. This is a really complicated way to detect an integer. But it's useful. So this leads to what I consider the most beautiful idea I've seen in mathematics. When I was a young postdoc at Ohio State, one of the senior professors asked me that question. I answered the circle method, and he said I was young, I would feel differently as I got older. I've seen a lot of math in the next 2 decades. I still go with the circle method. Because it allows you to attack problems you wouldn't think you could attack otherwise. So let's recall fn of x is the sum over primes up to n. Let's look at fn of x squared. So this would be the sum p1 less equal to n, sum of p2 less equal to n, e p1 of x, e p2 of x. Well, writing this out, it's the sum p1, p2 less equal to n, it's a double sum. And then I have e to the 2 pi I p1x, e to the 2 pi I p2x. Right? This is the same as the sum p1, p2 less equal to n of e to the 2 pi I p1 plus p2 times x. Now, proof by example. Somebody give me an even number. Good, big-sized even number. Not a small wussy. 4. 326. E to the negative 3. That's... I was wondering if people were actually going to say 2018, but I'm going to look at more space. Right. So let's integrate from 0 to 1, fn of x squared times e to the negative 2 pi I 326 x dx. So I'm going to take my function, and I'm going to integrate it against e to the negative 2 pi I 326x. So on this side, because I have a finite integral and a finite sums, I can switch the orders. Okay, this is the Fubini theorem. Have I shown you the video of Cam waving his magic bubble wand? At some point I will show you the video of Cam when he was 2 waving his magic bubble wand. I was teaching multivariable calculus, and I taught him, well, if you just wave your magic wand, it justifies your interchange. How many of you remember the Fubini theorem about when you can switch orders of integration? Okay. To do Fubini. All right. We will do Fubini later today. All right. You should be aware of the Fubini theorem. You should be aware that you cannot always switch orders of integration and stay a math major. There's other choices on campus, though. They're very welcoming. I will even give you a letter of recommendation. All right. So over here, I'm going to just switch everything. We have my double sum outside, p1, p2 less equal to n, integral from 0 to 1, e to the 2 pi I, p1 plus p2 minus 326 x dx. Let's look at this integral. What can you tell me about this integral? Yes?
It is 0 if p1 plus p2 is not equal to 326.
Yeah, if p1 and p2 is not 326, then I'm integrating sines and cosines that have a non-trivial period. Period 1, period 2, period negative 5, whatever. And if p1 plus p2 equals 326, it's 1. Thank you for using that finger. So this is just going to count the number of ways, using numbers that are at most, primes at most 326, that we can write 326 as a sum of two primes. That's our answer. We just have to see if this integral is positive. This is one of the most terrifying integrals in mathematics. Just because we write something down doesn't mean we can actually do anything with it. But it at least now gives us a hook. It gives us a way to attack the problem, which we did not have a moment before. We can now use some number theory and say, do we know anything about these sums? This is a terribly complicated function to understand because it involves sums over primes. Putting in the logarithms makes it a little bit easier to understand. That will change. This will now become a weighted number of representations. Well, I don't care if it's a weighted count that's positive. If the weighted count is positive, then the count is positive as well. All right. So do people understand that we just need to evaluate this integral? So the question is, how can you evaluate an integral like this, not just for a number like 326, but in general? So the idea is that most of the time, this function is actually pretty small. Occasionally, the function is large. And you break it down and you analyze very well what is happening when the function is large. And so I will just give you a little bit of a sense today as to how you do this. This is not a class in analytic number theory, but I just wanted to give you a flavor of, this is a class on problem solving. This problem stumped people for centuries. It was a monumental insight when people recast the problem like this. And they're using generating functions. We did generating functions for Catalan numbers. We did generating functions for Fibonacci's. And they were nice generating functions. And you got this nice closed form expression, and then you could deduce things. I do not want to be like your Calc 2 teachers who left you thinking you can integrate. I want to make sure you leave my class knowing that no. But I want to be honest, that most of the time when you write down generating functions, you will not have a nice closed form expression. And then what do you do in those situations? All right. So we want to study this function. So the first thing you might want to ask is, what is the average value of this function? What is its extreme value? I'm going to lie a little bit. If pi of x is the number of p is prime, p less than equal to x, this is approximately x over log x. So what's the largest my function could be? How large could it possibly be? Each of these numbers is at most 1. How many numbers do we have?
N.
We don't have n. We're summing over all primes up to n. Yeah, so it's basically, it's at most pi of n, which is about n over log n. That is the upper bound on the function. Lower bound? 0. All right. So we have a trivial lower bound. We have a somewhat trivial upper bound. Then we could ask, on average, how big is it? It turns out the average value of this function is hard to calculate, but the average value of its square is easy. If you know the average value of the square, roughly take the square root, and morally, that's not a bad idea. So let's calculate the average of the absolute value of fn squared. So what I would want to do is I would want to integrate from 0 to 1 of fn of x absolute value squared dx. And since I'm integrating over an interval of length 1, I divide by 1. All right, I'm not going to bother writing divide by 1. I don't divide by 1. All right. Well, here's the beautiful trick. This is the integral from 0 to 1 of fn of x times fn of x complex conjugate dx. Good. Is everybody familiar with complex conjugates? Okay. So, again, this is a chance to make sure you will not be one of the Williams students who graduates not seeing complex numbers, not knowing complex conjugates, and stuff like this. If z is x plus iy, the complex conjugate of z is x minus iy. And so when you draw things in the complex plane, if this is x axis and this is the iy axis, if I give you the point 2, 3, 2 plus 3i, then its complex conjugate would be down there. And if I give you e to the 2 pi I n x, its complex conjugate is e to the negative 2 pi I n x. And this comes from, the exponential is cosine plus I sine. And if you take the complex conjugate, the plus I becomes a minus I, and the sine of negative x is negative sine of x. So it comes from sine is odd, cosine is even. So again, this is where a lot of these trig properties come from. So this is the amount of complex analysis we need. Well, now, this is the integral from 0 to 1 of the sum p1 less than equal to n e to the 2 pi I p1 of x, sum p2 less than equal to n e to the negative 2 pi I p2 of x dx. Ooh. What can you say about this integral? So I've got e to the 2 pi I p1, e to the negative 2 pi I p2. Yes?
0 if p1 is not equal to p2.
Yeah, it's 0 if p1 is not equal to p2. So this detective function kicks ass, right? It reduces to the case when p1 equals p2. How many times does p1 equal p2? Yeah, pi of n. So this is just pi of n, or roughly n over log n. So this tells us the average value of the square is like n over log n. So we might guess that the Fn on average is maybe like the square root of n over log n, because it's squares of size n over log n. What this is telling you is there's a lot of cancellation. How many of you have taken a probability class or a statistics class where you do the central limit there? If you flip a fair coin, n times, you should have about n. Well, let's flip it 2n times. If you flip it 2n times, you should have n heads, n tails. If a head is a +1, a tail is a -1, you expect to be at the origin. And you expect your fluctuations to be on the scale of square root of n. That there's cancellation at the level of square root of the number of terms. That's essentially what we have going on here. It's essentially a square root cancellation. It's essentially a central limit type argument. So this tells us that on average, the function is small. It could be as large as n over log n, but frequently it's much, much larger, much, much smaller. Let's look now at some special values. What would be the easiest place to evaluate Fn of x? Easiest. Easiest. 0. Right? Fn of 0 is the sum p less than equal to n of e to the 2 pi I p times 0. All right, well, anything to the 0th power is 1, so this is just going to be pi n, or about n over log n. All right. I could evaluate this at 1, but because the function is periodic with period 1, evaluating it at 1 is not a big deal. So this also equals Fn of 1. What's the next natural point to try to evaluate it at? I'm sorry? No, because I'm going to say 2 is the same as 1. Because it's periodic, yes? I'm sorry? N is the same as 2. Right? All the integers are the same. When you put in any integer here, you get n over log n. So you can't give me an integer. I need the next natural logical point. And this is why I don't want you preparing for class. Well, we got to evaluate at a real number. We integrate from 0 to 1. A half, right? That's the most natural place. And then after a half, what would be the next point? I'm sorry?
Root 2.
Not root 2. Root 2 terrifies. Root 2 is irrational. That'd be like putting on one pair of pants and then putting on. Sorry. What did you say? A third, and then 2/3, and then a fourth, and then 3/4, and then a fifth, 2/5. Keep doing rationals like this. So if we do Fn of a half, we now get the sum p less than equal to n e to the 2 pi I p times 1/2. Well, if p is the even prime, then we would get e to the pi I times 2, right? Well, that's going to be e to the 2 pi I, that's going to be 1. And then if p is an odd prime, well, the 2 and the 1/2 cancels, and we have e to an odd multiple of pi I. That's going to be minus 1. So we would get minus pi of n minus 1. So this is approximately negative n over log n. If you want, it's negative n over log n plus 2. But the size of it is about n over log n. If I look at fn of a over q at some rational, then what I get is this is going to be the sum, p less equal to n, of e to the 2 pi I p a over q. And now when you look at this, this only depends weakly on p. So for those of you who've seen abstract algebra, how does this depend on p? So I claim a lot of different p's will give the same value. Every time p increases by q, I return to the same value. Because I'm dividing by q. So if I increase p by q, say I increase it by 2q, I've increased this by 2, well, 2 times 2 pi I, that's just 4 pi I. I've just done an integral number of periods away. So this is going to be the same as the sum of the following. Look at R mod q, and then sum over p congruent to R mod q of e to the 2 pi I RA over q. And this is over primes at most n. Well, it turns out now this has no p dependence. So you can pull this out, and you get a sum of R mod q. Then you get e to the 2 pi I R A over q. And then you get the number R Q n. So this will be the number of primes congruent to R mod q. And if q is small, that should be large. We talked a little bit about, I think, Dirichlet's theorem, primes in arithmetic progression. But the idea is to just show you that there's a chance of analyzing this with standard number theory functions. That as long as q is small, I can actually control this, and the function is large. So most of the time, the generating function is small, and so you can say, forget about it. It doesn't really contribute. And then occasionally it's really large, and it involves number theory functions. They're involved, but there are techniques to handle them. And so again, what I wanted you to get from this lecture is an idea of how to attack problems like this, that there is a way. If you are interested, email me, and I will give you some notes to read on how to do this more rigorously and what the challenges are. But the idea is these problems are not inaccessible. There are ways to attack them. We can solve problems like this. All right, so for the last few moments of class, I want to just quickly review Fubini's theorem about when you can change orders. So for Fubini, basically, if you have a double integral, or a double sum, if the integral, a to b, integral c to d, of the absolute value of f of x, y, dx, dy is less than infinity, can switch. That's a really good condition. Essentially, the difficulties in mathematics almost always come down to, am I using infinity somewhere? So I will quickly give you an example of a situation where you cannot switch orders of integration. Instead of doing orders of integration, I'm going to do a double sum. If you don't like double sums, either tough luck, or if that's too harsh, I will then say you can smear them out and make them continuous distributions. All right. So let's imagine all the dots in the upper quadrant. In the interests of time, I will only draw a finite set of them. If you would prefer more, by all means, draw some later today in your other classes. All right. So this will be the point 0, 0. This will be the point 1, 0. This will be the point 2, 0, and so on and so on. And I'm going to define a sequence A and n as follows. +1, -1, and then 0 for the rest of eternity. 0, plus 1, minus 1, and then 0 for the rest of eternity. 0, 0, plus 1, minus 1, and then 0 for the rest of eternity. Okay? Let's look at the sum. M goes from 0 to infinity. The sum n goes from 0 to infinity of a m n versus the sum n goes from 0 to infinity. The sum m goes from 0 to infinity of a m n. So in this one, I first fix m. So I first fix a column. What can you tell me about the sum of every column? 0. So if I sum 0 infinitely often, what do I get? 0. Okay. In this one, I first fix it in. I fix a row. What's the sum of every row? 0 except for the first one. The first row sums to 1. Every other row sums to 0. Right? Exercise. Prove 0 does not equal 1. Right? Depending on what you're allowed to use, that is not always an easy problem. This proves that you can't always switch the orders. And if you don't like this, you can make your function like a tetrahedron or something, or a box coming up, down, and going down, or circles, or hemispheres. There's lots of things you can do. This is my favorite example of showing why you have to be careful in switching orders. And there's a lot of infinities in this. One infinity is that the region goes off to infinity. Another infinity here is if you put in the absolute value, the sum of the absolute value is plus infinity. So if you want to switch orders, you need to be able to justify it. And this is a terrific example. If people remind me for the next class, I will start off with the video from Cam.